Good evening, everyone. Welcome to the NPTEL course Real Analysis 1. This is our 12th problem solving session. I am Amrita Case and I am a PhD student at IIT Kanpur. So let's start the session. So in week 12, there are no exercises. Week 12 is related to the Weierstrass approximation theorem, but there are no exercises in the notes shared. So let's do some other exercises. Which involves the Weierstrass approximation theorem. So the first one is, if f is continuous on closed 0 1, and if integral 0 to 1 f of x power n dx, this is 0 for all n equal to 0 1 2 and so on. Then prove that f of x is 0 on the interval 0 1. So let me recall the Weierstrass approximation theorem. The Weierstrass approximation theorem says that if you have a continuous function on a closed interval a b, this is continuous, then f can be uniformly approximated through a polynomials, right? So that means there exists some polynomials Pn that converges to f uniformly on that interval. Okay. Now for this question, you should prove that f of x is 0. So here it is given that this integral is 0, right? So what can we conclude from this? So integral 0 f of x power n. dx. This is 0. This is a 0 for all n from n 0, 1, 2 and so on, right? So this implies that whenever we take a polynomial f of x times p of x dx, this is 0, right? For all polynomial p, right? Because whatever polynomial we have, it would have it would be of this form, right? Summation some a n x power n, and once we expand the sum, we would see that this is 0 for all polynomial p. This integral is 0, right? Now it is enough. It is enough to show that integral 0 to 1 f of x squared dx, this is 0, right? Because I think this we have done as an exercise in Riemann integrals. This is because um, f square, this is positive, not the composition but just square. This is positive function, and if this is positive, then integral oh sorry, this is non-negative function. Yeah, this is non-negative function, and if suppose some at x naught, if this is greater than 0, then this would imply that on this interval this is greater than 0, greater than or equal to 0. So please recall this exercise. So this would imply this this thing this thing would imply that f of x is 0 on the whole interval. Okay. Now we will try to show this. Yeah, but here we only know about this integral, and the Weierstrass approximation theorem comes to our help. So by Weierstrass approximation theorem, there exist some Pn polynomials that converge to f uniformly, right? So we can write 0 to 1 this is equal to, I am replacing f square x by f of x times p of x. Sorry, Pn of x. Limit Pn of x. Right? Now this is, I can take limit outside because it is uniform convergence, right? Because of uniform convergence. Now we know that we have already observed that this integral is 0, right? This is 0, and therefore this is 0. Therefore we see that this integral is 0, right? And therefore f of x is 0 on the whole integral. Okay. Now another application is that I don't think yeah, one can prove that suppose this is the set of all continuous functions on 0 1. Then this is separable. I don't know whether sir has taught separability or not. Let me just check. Yeah, I don't think separability has been taught, but I hope the ones who are seeing this, ones who are watching these lectures, they might be familiar with separability. By separability, we mean that suppose if A is separable, we mean that there exists a countable set in A. There suppose B it's a subset of A which is countable such that B closure is A. An example is rational, the real numbers. Real numbers are separable because we can take rational numbers. We know that the closure is R. Yeah. So the Weierstrass approximation theorem helps us to show that the set of all continuous functions on 0 1. 0 1 does not matter. Any compact set in R is separable. To see what is that countable set, one can take uh, all polynomials. Suppose I define P to be a set of all polynomials on 0 1. Yeah, set of all polynomials on 0 1. Then if we take the closure, yeah, here by closure we mean uh, those functions that are uniform limit of polynomials. Okay, here the closure. So here, just try to see what is meant by closure here. Okay, so using the Weierstrass approximation theorem, this is just continuous functions. Yeah, this is just C of 0 1. Means uniform limits of polynomials. Note that by closure here we don't mean the point-wise convergence. Here we mean the uniform convergence. Okay. So this is this. Now one should show that the set of polynomials on 0, 1 is countable. Yeah, but that is not countable. This is an uncountable set. But a subset of it is countable. For example, set of all polynomials on 0, 1 with rational coefficients. But then, if we take rational coefficients, one can uh, always approximate the set of all polynomials with um set of all polynomials with rational coefficients, right? This is because the rational numbers, they are dense in real numbers. So that means the closure of this set as well would give me this. Okay. Uh, so please write down and see and try to understand. Please note that we are not taking the set of all polynomials. Okay. Now we will show that this subset of polynomials is countable. Um, to show this, first note that suppose n is the degree of p. N is the degree of a polynomial p. Then we show that suppose I take Pn to be set of all polynomials on 0, 1 with rational coefficients and of degree p. Sorry, and of degree n. Then I would show that this set is countable. Okay, once I have shown this, I know that the set of all countable set of all countable union of countable set is countable, implies that p is countable, right? Okay. Now suppose I take a p from the set, then p is of the form p of x can be written as some a n x power n, so on, a1x plus a naught, right? Now see that there is n plus 1 rationals here, right? So I can define all the polynomials in Pn by deciding my coefficients, right? So I just need to pick some n plus 1 rational numbers and decide my polynomial, right? So that means these are just finitely many uh, yeah so these are just finitely many, right? So then that means here there are countably many possibilities, here there are countably many possibilities, and so on, right? That means there are n plus 1 countably many possibilities. So that means uh, finite union of countable sets is countable. So this implies that Pn is countable. Okay, so please write them down and try to understand. Okay, so this would imply that we have a countable set whose closure gives C01. This would mean that C01 is separable. Okay. Now one can ask numerous questions about the theorem. Like by the rest as the theorem statement is that f is continuous on a comma b, right? Closed a comma b. Then there exist polynomials Pn that converges to f uniformly, right? So what is the importance of this closed and bounded set here? Like, can one draw uh, maybe the closeness or the boundedness and still get same results? But that is not possible. One can get counter examples. Yeah, for example, uh, suppose I take 0 1. Then what can go wrong? Or if I take r, then also what can go wrong? Okay, this is not closed and this is not bounded. For example, you can take f of x equal to 1 by x on 0 1. Okay. Now this is continuous. Yeah, this is continuous. But one should prove that there does not exist. There does not exist polynomials Pn that converges to f uniform. But this is easy to see because suppose I take Pn's on 0 1, then they are bounded, right? All of them are bounded. Now suppose if Pn converges to f uniformly, then last class Yeah, or two classes back, we saw that this would imply that f is bounded. Oh, sorry. Oh, sorry, there is something wrong. It should imply that f is bounded on 0, but this is not possible, a contradiction. So this would imply that there does not exist there does not exist a sequence of polynomials that converges to f uniformly. Now one can argue that so here one can see that uh, the uniform continuity is helping here, right? Because once you have a compact set, you would automatically have uniform continuity, right? But here you do not get uniform continuity. But still, uniform continuity is not enough, because once you take R and f of x equal to sin x or cos x, you know that this is uniformly continuous. But still, one can argue that the result does not hold here. One can prove this using the zero set of sin x. This is because sin x um, sin x, if you take sin x is 0 whenever x is n pi, right? But then the polynomials, they can have only finitely many zeros, and therefore the one would not get uniform convergence there. One can write that down and see. Um, because this is because like sin x will be like this, right? At n pi. But if you take polynomials, of course one should write it down properly. But the idea is that if you take polynomials they have finitely many zeros, and when x goes to plus or minus infinity, Pn of x also goes to plus or minus infinity, right? According to the coefficients, according to the leading coefficients. So what happens is this sin x, uh, they would be around these things, around the yeah in between -1 and 1, but the polynomials, they would go unbounded. So all these things gets violated, and one can see that sin x cannot be uniformly approximated through polynomials. Okay, please write it down and see. Yeah. So then let's do some general exercises. Yeah. So this is an easy exercise from continuity. Mm, So let A be, let them be subsets of R. F is from B to R, and let G be a restriction of F to A. Now the first question is if F is continuous at A. If F is continuous at C in A, then show that G is continuous. G is also continuous at C. Uh, so this is easy because the same delta works for every epsilon, right? You just need to intersect it with A. Now the next part is show by example that G is continuous at A. Sorry, G is continuous at C in A. This need not imply that F is continuous at C. easy example is to take the Dirichlet function. One can take f to be the Dirichlet function on R. Then you can take A to be just Q. Then one can see that f is, if you take any rational number, C to be any rational number, then you can see that g of x is just 1, right? For all x in A. Then one can see that one can see that g is continuous, right? Because here it is just the constant function, but f is not continuous, right? Okay. Now let's see some examples related to the Lipschitz continuity. Lipschitz functions. We know that Lipschitz implies continuity, right? But it is not the case that the other way is true. Sorry, Lipschitz implies uniform continuity. Uh, let's see an example for that. For that, let's take g of x to be root of x. Okay, and we take mm, x from 0 to. Okay, now since g is continuous, okay, we know that g is continuous and the set is compact. This would imply that g is uniformly continuous. Now we will show that g is not Lipschitz. Okay, g is not Lipschitz on this interval. That is, there does not exist uh, there does not exist a case such that g of x minus y less than or equal to k times for all x comma y in this interval. Um, for example, let's take y equal to 0. Then in that case, g of x is just root of x. Right? So we need this to be less than or equal to k times mod x, right? Yeah, so is this true? Let's take it like, is this true for some k? For some k. So if we take x to be 1 by n. Then what do we see? This is root 10 less than or equal to some k times n, right? That means here you would get root 10 less than or equal to k. But this is not possible, right? Because n is unbounded. So that means that there does not exist a case such that this holds. So this implies that this G is not Lipschitz. Okay. Now the let's see some algebra of Lipschitz functions. Suppose if f and g are Lipschitz functions, then what about some f plus g? And can easily show that this is Lipschitz, right? Because if k1 corresponds to the constant with respect to f, and if k2 with respect to g, then one can take um, and one can apply the triangle inequality and do that, right? Mm, okay, let's see. You need this f of x plus g of x minus f of y minus g of y. Okay? This is less than or equal to f of x minus f of y plus g of x minus g of y. This is suppose we have a k1 and here we have k2. This is equal to k1 plus k2 times mod x minus y. Right? This is easy. Now what about product? Is the product Lipschitz? So this is not true actually. One can find a counterexample. So this is true if f and g are bounded on it. I think we have seen similar kind of results for uniform convergence of functions, I guess. For this, it is just to use some inequalities, that is um, the same kind of things actually as we saw for convergence of functions. Then one will just add and subtract uh, f of x, f of I think, yeah, f of x g of pi, I guess. And then apply the triangle inequality. And then here, because f is bounded on a, we can take out the supremum of this f of x. Here one can take out the supremum of g of pi and then use the Lipschitz property of f and g, and then you would get it readily. Now if it is not bounded, it is not necessary that you will get the product to be Lipschitz. For example, you can take f of x to be x. Then one knows that this is Lipschitz, right? Because one can take the constant to be 1. Now, if you take the square, this is x square and x is from R. Or you can take from 0 infinity. Then one can show that this is not Lipschitz. If you take mod of x square minus mod of y mod of x square minus y square, then this is mod of x minus y times x plus y, right? Now the thing is, this thing cannot be bounded by any constant. Okay, one can show that this is not Lipschitz. Let us solve another exercise. Hmm. Let A be a subset of R, and suppose that F from A to R has the following property. That is, for each epsilon greater than 0, there exists a function g epsilon from A to R such that g epsilon is uniformly continuous. Hello, Equip.
Yes.
Yeah, I was doing some extra questions.
Okay. Okay.
Yeah, I did some questions related to Lipschitz functions. Now I started with another question. Okay.
Okay.
Do you have any doubts or questions related to the week 12 content?
No.
Okay. So it was just about Weierstrass approximation theory, right?
Yeah.
Okay. Now here is a question. Suppose A is a subset of R and F is from A to R. Okay,
Yeah.
and F has the following property. That is,
Okay.
for each epsilon greater than 0, there exists a function g epsilon from A to R such that g epsilon is uniformly continuous on A and f of x minus g epsilon of x. The mod of this is less than epsilon for all x in A. Prove that f is uniformly continuous on A. Yeah, is the property clear?
Yeah.
Hmm. So that means you should somehow uh, that means you should show that for all epsilon greater than 0, there exists delta greater than 0 such that this is less than epsilon whenever mod of x minus y is less than delta. You know that g epsilon is uniformly continuous on A, and this is also true. Now, how to get this?
Mm, So take epsilon greater than 0.
Hmm. Hmm.
Uh, And suppose xy belongs to
Hmm.
A.
Hmm.
Now mod of fx minus fy
Hmm.
is less than equals to fx minus g epsilon x
Hmm.
plus
Hmm.
uh,
Hmm.
g epsilon x minus g epsilon y
Hmm.
plus g epsilon y minus fy.
Hmm. Hmm.
So
But that's right.
yeah,
Hmm. Hmm.
uh, so the so less than what is given for all. So less than
Hmm.
g epsilon
Hmm.
whenever uh, mod x minus y less than
Hmm.
half
Hmm.
delta.
Huh. So in that case, now if this is true, then there exists the epsilon
Yeah,
such that this holds, right? Such
yeah,
that the properties hold.
yeah.
So that means there exists a delta greater than 0 such that g of x minus g of y, sorry, g epsilon. G epsilon x minus g epsilon y is less than epsilon whenever delta, sorry, mod x minus y is less than delta. So we get this whenever less than delta, right?
Yeah,
So that means for all epsilon, we can take the same delta. This
yeah,
implies that f is uniformly continuous, right?
yeah.
Hmm. Okay. Now another question. You know periodic function, right?
Yeah,
F from R to R, then f is periodic if there exists a number p greater than 0 such that this holds f of x plus p is equal to f of x, right? For all
mm,
x in R. P is the period there. Then prove that a continuous periodic function on R is bounded and uniformly continuous. F is continuous and
mm,
periodic implies f is bounded and uniformly continuous on R.
okay.
Hmm.
So
Hmm.
and if we prove in the closed interval 0p,
Hmm.
uh, if f is bounded on
Hmm.
zero closed interval 0p, then I think
Hmm.
it is bounded.
Hmm. Yeah. Yeah, that is the idea.
Yeah.
F is bounded on 0p implies F is bounded on R. Right?
Yeah.
Because if I take any
Because
y in R,
yeah.
then y can be written as some m times p plus x, where x belongs to this interval, right?
Yeah.
Then f of y is just f of x. And that first is bounded, right?
Yeah.
Hmm. Now what about this? F is bounded on 0p.
Hmm. Now f is continuous on 0p.
Hmm. Yes.
So f is
Hmm.
uh,
Hmm.
bounded
Yeah. If
on 0p and so.
continuous on 0p implies this, right?
Hmm. And I think uniform continuity also
Hmm.
follows likewise.
Hmm.
Uh,
Hmm.
so if we take any uh, xy in 0p,
Hmm. Any x, y.
no, suppose xy any from R, okay,
Okay.
from
Sorry.
xy belongs to R,
Ah.
uh,
It is not working properly.
then we can find some x dash.
Hmm. Which one? X dash.
Yeah,
Hmm. Okay.
uh, comma y dash belongs to 0p
Hmm.
such, such that
Hmm.
uh, x equals to
Huh.
mp1,
Hmm.
sorry, uh,
Huh.
m1p plus
Ah.
x dash.
Huh. You can just write this. Ah. I understood. This,
Okay.
right?
Yeah.
Hmm. Hmm.
Now,
Then.
uh, fx minus fy.
Hmm. Oh, just a minute. It is not working properly. My pen. Huh. 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 This is equal to. Huh. Yeah. Huh. Now.
So, if x minus y less than delta,
Huh. Huh.
sorry, we have to show that x minus y. Okay.
Hmm.
Whenever x mod of x minus y
Hmm. What of x minus y?
less than delta,
Okay, what is your delta?
we have to choose the uh, uh, on 0p, f is uniformly continuous. Okay,
Yeah, f is uni- uniformly continuous.
on 0p.
Hmm.
So for for given epsilon greater than 0,
Hmm.
there exists delta
Huh.
greater than 0
Huh.
such that
Huh.
fx minus fy less than epsilon
Hmm.
whenever x minus y less than delta.
Then delta, but x and y are from 0p, right?
Okay.
Hmm.
Uh, there is some should be. I think x minus y less than delta
Hmm.
implies x dash minus y dash less than delta. Is it true?
Um, x minus y. No, I don't think so. Because if you take, suppose this is your 0p, okay, 0p.
Two adjacent
So
nodes.
if you take, no, these are of p width. You can take x here and y here, right?
Okay.
Still, you might get x dash minus p dash to be less than delta, but x minus p is never less than delta.
No, I try to say that if x minus y less than delta,
If
then x dash minus y dash
if x minus y less than
mod
delta, then
then mod x dash minus y dash
uh,
less than delta. Is it true?
no, x dash y dash are from these intervals, right?
Is it y dash? Yeah.
So if you take x dash to be 0 and y dash some 0 plus delta by 2. Okay, if you get something like this, then what should you take? X to be, you can take some 10th p and y to be delta by 2, right? Still, you will get this. But x minus y is not less than delta.
I am trying.
Like you
Then
understand?
yeah, then it is vacuously true.
Vacuously true.
I try to say that if mod x minus y less than delta holds,
Huh.
then x dash minus y dash less than delta. Is
Huh.
it
Huh.
true?
Huh. Okay, that is true. Huh.
I think it is true. Only problem is there. Suppose you take mm, x from one interval,
Hmm.
the you just
Yeah, I understood. If you
scale
take,
down 0p some 0p. Yeah, and adjust it. Yes,
hmm.
only this case should be taken care of.
Hmm. 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 Yeah, this then x might go here and y might come here maybe. Yeah. No, y
Mm,
might come here. X might go here. Yeah. This might
it
not
may
be.
happen.
Huh?
It may happen.
Yeah, this may not be true. Hello.
Yeah.
Yeah, this may not be true.
Okay. Okay. So may not be true.
Hmm.
Then how we?
Hmm.
If it is true, then it is done because mm, you go there.
Hmm.
Yeah, because then we can say that if x minus y less than delta, then x dash minus y dash less than delta, and then if x dash minus fy dash less than epsilon.
Hmm.
Understand? Huh?
Yeah, yeah.
So now you say that this may not be true.
Yeah, no, you need to see how these things needs to be taken care of. Like whenever this is not less than delta,
Whenever
this is
x
not less
minus,
than delta.
x minus y less than delta, but x dash minus y dash may not be so. Uh, mm, period is p, so fx plus p equals to fx. Okay. So
Hmm.
uh, I think suppose there is common MP,
Hmm.
then we have to somehow manipulate uh, fx minus fmp plus fmp minus fy.
Uh, uh, can you please repeat? Hmm.
Suppose
Hmm. Hmm.
x equals to
Hmm.
x dashed
Hmm.
plus mp
Hmm.
and y dashed equals to
What?
y equals to y dash plus mp.
Huh.
There has to be same mp because
Why? Oh, you want same NP?
yeah, because if
Hmm.
mm, I think we can take delta less than p.
Delta. Okay. Yeah.
So mm, only case when xy may uh, distance of xy means a mod of x minus y.
Hmm.
If these are distinct mp and np, then I think mod of x minus y will be greater than p.
Dog.
Minus y greater than p. If you take mp and np,
Okay.
only case that that makes problem can be the same mp.
Uh, uh,
Only case
hmm.
that may be problematic is same mp when they are adjacent, I think. Okay, but no, I may be wrong. They are adjacent by, but the expression should be, what should be their expression if they are adjacent?
So maybe you can take 2p, right? If I take 2p, then I know that on 0 to p also it is uniformly continuous. Then I can find some other y dash such that I can find x dash here and y dash here,
Okay,
right?
okay.
The problem comes when you try to, uh, or maybe I am wrong.
So you are taking mod of x minus y less than delta wherever in this. So
Right? The problem is when you have x, suppose if these are my p intervals, this is my 0p, and if I take some x here and y here in with delta distance, then it can happen that x dash comes here and y dash comes here, right? And this
yeah,
distance might be greater than delta,
okay,
right?
yeah.
But if I take 2p, here also it is uniformly continuous, then I can find my y dash here, right? Such that x dash minus y dash is less than delta or delta. This I can avoid.
No, what you want to understand? Why dash is so?
Because here in 0 to 2p I can find y dash, right? Near to x dash.
So you uh, they may be, but how you can be sure that some y dash is there so that x dash minus y dash less than delta?
Hmm?
how are you sure that y dash can be chosen so that x dash minus y dash less than delta?
Mm, see, the thing comes here is let's take x less than y. Okay. Then in that case, what happens is, mm, suppose if both x and y belong to uh, this thing. Okay. Mm, because the thing is, first you find y dash. Hello.
Yeah.
First you find y dash inside this interval. Okay. That you can do y dash here. Huh? Then you
Mm,
add p.
okay.
Then you will get y double dash, right?
Okay.
Then you can see that x dash minus y double dash is less than y double dash minus x dash is less than delta.
How it is so?
How means, see, what about y dash here? Why does there exist y dash?
Y dash in between 0p.
Huh?
In between 0p.
Huh.
I think the x between x and y there is some point we should use that
Huh?
mp kind of mp or mp kind
Huh.
because because then it can be um, if it is x minus y greater than delta.
Which one?
If this
X minus y
minus y greater than delta,
greater than delta.
yeah, we only think about this, is not it?
No. We are starting with arbitrary x and y, right?
Yeah.
Oh, you want this x dash minus y dash greater than delta. That is what you want. So
Okay.
what are we planning to do? You get some delta from this interval, right?
Yeah.
Then you want to show that this delta works for r as well, right?
Yeah.
Yes. So what can go wrong? When you take x and y in r,
With mod of x minus y less than delta,
huh?
it may happen that x dash minus y dash greater than delta.
Yeah. But in that case, you take y double dash to be y dash plus p.
Okay.
Then you will get y double dash minus x dash to be less than delta. But
We,
then you should apply uniform continuity on, you should take delta.
okay, but how it is so? Y dash minus x dash less than delta.
You can see
Y
it,
double dash
right?
minus x dash.
Just try to show it from the figure. What
Yeah, y dash. But here are p and delta. There are two things. Okay.
there is?
There are two things we have to handle. X and y dash, they are 0p, and whenever you add p, that may
So you
mm,
push x. Okay, you push x to this interval 0p. Okay, that means you take x dash. First of
suppose
all, you can
suppose
find x dash,
you
right?
take you take p equals to 1. Okay.
Huh? No, I'm telling you. You are sure that there exists x dash such that uh, x dash is in 0p, right?
Okay.
Huh? Now take
Okay.
y double dash to be what? X dash plus y minus x. What is y minus x? This distance. Okay. And here you get x dash. Add that distance. You get y dash, y double dash. And y double dash is in 0, 0 to 2p.
A 0 to 2p.
Yeah.
Yeah, that is right.
Yeah. That is what I am telling. Oh, you are not seeing this 2p maybe. This is 2p. Here is my p.
No, you are telling that y dash minus x is less than delta.
Yeah.
That may not true.
No, no. I am telling y double dash. See.
Yeah, yeah, y double dash minus x is less than delta. That may not be true.
Y. What is this? You
Suppose,
are defining y double dash. You are defining y double dash to be this, right? Then what is this? Y double dash minus x dash is exactly mod of x minus y. This is less than delta.
okay, okay. So you y double dash is not x dash plus p. X dash plus y minus x. Okay.
Huh.
You are mm,
Because that would correspond to the y here.
okay. Now what you want to show that?
So this is the corresponding to y. You can show that this is equal to this. This is double dash.
Y. You are not adding your choice of y double dash.
Hmm. What? From the figure itself you can see, right? F of y is equal to f of y double dash.
Look, when you take y double dash equals to y dash plus some kp, then it is true. But you are taking y double dash equals to x dash plus something.
No, see, I am just adding the distance. That is all. Either way you can go.
Okay, okay. Then
When I try telling you using y dash thing, you told that it is not making sense to you. That is why I wrote it like this. Either way you can do it.
so you are telling that fy equals to fy double dash. So it actually, in order to it to happen, in order to if to happen fy equals to fy double dash,
Hmm.
y must be y double dash plus something into p.
Why? Okay. For this to happen, you need y double dash to be
Ap plus y.
kp plus y.
Yeah.
Yeah, yeah, it is exactly this. You know that you would get y dash, right?
Yeah.
Then add p to it to get y double dash.
No, you are not taking p.
What
You are adding
p?
y minus x.
Huh?
You are adding.
Hmm. It is the same.
I cannot understand. Okay.
See, it is the same distance.
Y minus x.
See, either you define y double dash to be p plus y dash, or you define y double dash to be x dash plus y minus x. It is the same only. No, you don't understand. Okay, you take p to be 1. Okay, take p to be 1. 0, 1. Okay. So what can go wrong? Now this is your minus 1. This is your minus 2. This is your minus 3. Okay. Okay. Hello.
Yeah.
So what can go wrong? It can go wrong if it is some minus 3.9 x. Okay. And y is, oh sorry, 2.9, and y sorry, 2.1, and y is minus 1.9. Okay. Then this is my x. Sorry, what is it? This is my x. This is my y. Then what is my x dash? X dash is what? 0.1, right?
Yeah.
Mm, is that so? No, 0.9, right?
Yeah.
0.9. And this is my x dash. And my y dash will be what? My y dash will come here, right? Y dash
Yeah.
will be some 0.1, right? This is
Yeah.
my y dash. So here what happens is this distance can be greater than delta.
So now,
Huh.
uh, suppose delta equals to 0.1.
Now I take y double dash to be this
Yeah.
1.1, right? That means I am adding p. Or it is that I just take this to be y dash to be just y double dash to be x dash plus this distance. It is just the same.
Okay. X dash plus. Oh, it is same thing.
Yeah.
Okay. Okay.
Okay. Now, but the thing is, you should take the delta corresponding to the uniform continuity on 0 to 2, not 0 to 1.
Okay.
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 Okay. So maybe we can do one more exercise. Hmm. So, are you aware of that continuous function which is not differentiable anywhere? Mm, F is uh, defined on 0 1, continuous, but nowhere differentiable on 0 1.
Nowhere differentiable.
Hmm. What? Okay. Let me ask one more question. I was thinking about it during this exercise. So here you are taking f is continuous on this, right? On closed
Yeah.
0 p to f. So that means you need closed. It should be closed plus bounded.
Yeah.
Can you drop closeness to get f is bounded?
So you mean if is continuous
Hmm.
on open interval, open bounded interval?
The thing is, f is continuous on closed plus bounded will give f is bounded.
Yeah.
So I'm asking whether f is continuous on
On open interval.
on bounded.
Uh, no, it is may not be bounded because
Huh,
you take f 0 1 open 0 1 to r
huh,
if x equals to 1 by x,
yeah, good. Now if you take closed,
but not bounded.
hmm,
It is also not unbound. It is just identity taking identity
huh,
function.
yeah, okay. Mm, huh. Now what about this? F is continuous. Um,
If it's continuous everywhere,
yeah, F is continuous
but
everywhere,
no
but
have differentiable. I know there exists some function, but
huh.
uh, I
What if
don't know
F
that
is
function.
monotone?
Uh-huh.
What if I add monotone?
Continuous plus monotone.
Yeah,
Continuous plus uh, mm, so monotone function. I think
hmm.
So if that function may be differentiable or not.
No, I'm asking whether there exists a continuous. You know that there exists a continuous function which is nowhere differentiable.
Okay.
But I'm asking whether there exists a continuous monotone function which is nowhere differentiable.
It may exist, but it should be very bad kind of function.
Actually, it
In,
does not exist.
huh?
It does not exist.
Does not exist.
Yeah,
O-
let me get the theorem.
Okay.
Yeah, it does not exist. Just because for monotone function, the points where it cannot be differentiable, that will be countable actually.
That will be.
Countable. Or
Yeah, yeah,
uh,
yeah. Monotone function point of discontinuity
huh.
is countable. Yeah,
Oh, it is discontinuity.
yeah.
Okay, then I am wrong. Oh, I was trying to find the theorem. Okay, then you can leave it. Yeah, if it is continuous, then set of discontinuities are countable, right?
Yeah.
Okay. Huh. So then, let's see this. Let's look at this function. It is little interesting.
Yeah.
This thing. It is continuous but nowhere differentiable.
It exists, but I don't know the function.
Yeah. Let's just look at that. Like the idea.
Uh, Nowhere differentiable means so each point there is
Hmm.
some corner thing.
Yeah. So if you take 0, 1.
So each
Yeah.
there is in each
Uh,
point there is some step kind of thing.
hmm. Yes. So this is it. So this function can be represented as a limit of some functions. Okay.
Continuous function.
Yeah. Limit of some continuous function. Uniform.
Yeah, yeah,
Uniform limit of continuous functions.
yeah.
This is continuous, right? So
Uh,
therefore,
Uniform limit of continuous
functions is continuous. So therefore, our f should be continuous.
differentiable function.
Huh? Hello?
Uniform limit of different continuous function.
Huh. What is the confusion? Hello?
How it is so?
Huh?
How
Uniform
it is so?
Fn converges to F uniformly.
Okay.
Fn's are continuous. And this implies that F is continuous, right?
Yeah.
Huh. It is the same statement.
Yes.
Or
You are you are saying that f is uniform limit of continuous function. Oh, is continuous. Okay, okay, okay. I think you are telling that any continuous function is uniform limit of some continuous. Okay, it is.
no. Huh. So the thing is, this is our F1, and then we divide it into 4 intervals. Now, if this is 1 by 2, we take 1 by 4 and then draw peaks here. Okay. And then take 1 by 8 and then again draw peaks like this.
Okay.
Hmm. And then, so these are our FMs. FMs are, this is our F naught. Okay. Then FMs are power M, F naught is X.
Okay.
Hmm. Then, then we see that this is continuous, right? FMs are continuous.
Hmm.
Now, uh,
So, how you calculate the this function?
it is there in the text. You know this Robert G. Bartle and Donald R. Sherbert.
Okay, okay,
There in Appendix E.
okay.
Appendix E. Then what happens is,
So you are taking fm equals to this,
hmm,
uh, where f0 is a continuous function.
yeah, like this big mountain.
Yeah,
So this is not differentiable at 1 by 2.
yeah, yeah,
Now these things are not differentiable here.
yeah. One by
Uh-huh.
mm,
Hmm.
1/8, I think.
Hmm. Hmm. Hmm.
1/8, 2/8, 3 by
Hmm.
no 1/4, 2/4, 3/4.
Hmm.
This kind of thing.
Yeah. And then we define a function g of x.
Also,
Hmm.
they are not differentiable at 1/8 also.
Yeah, these points. Yes. Hmm.
1/8.
1 by 16, 1 by 8. Yeah. Something.
Okay, okay.
Hmm.
So you are now you take the limit.
No, we are telling that it is our g. Okay. We are defining g to be 0 to infinity fm of x.
Okay.
Then it is the uh, limit of continuous functions, right? We
Okay.
know
So
that fm's are all continuous.
yeah.
Hmm.
Now,
And then
so mod of this less than equals to 1 by 4 to the power m.
hmm, finite
Uh,
sums,
okay.
they are continuous.
Oh, yeah, there is some test. I mean test.
Yeah. So this converges, and that is why
Yeah.
we have this, so that it can converge. We know
Okay.
that
Okay.
f0 mod of this is less
Less than 1.
than 1.
Okay.
And here you have 4 here, 1 by 4 here, and therefore it converges.
So this function is continuous.
Yeah,
Now you are saying that this is nowhere differentiable.
yeah, this is nowhere differentiable.
So you are adding.
Yeah,
What
we
is
are adding.
f1 means 1 by 4 into f0 4x.
Hmm. Yeah, it is kind of complicated.
Hmm. So you are telling that this is nowhere differentiable.
Yeah, this is nowhere differentiable.
Okay.
Hmm. This is because the slopes and all they will create the problem.
What?
These slopes here
Hmm.
they will create a problem actually.
Yeah.
Hmm. Yeah, we are taking some because otherwise these fm's will go to 0, right?
Yeah.
Hmm. Yeah. So it is time I should go somewhere. So maybe we can continue this in the next class. Actually, I have scheduled a class on 13th from 6:30.
Is there any class
No, this is our 12th
after?
lecture.
Okay.
So you it will be announced. On 13th, there is a class from 6:30 to 7:30.
13th.
Yeah, 13th.
7:30 to.
No, 6:30,
Okay. 6:30 to.
7:30.
13th means Sunday, Monday.
No, is it Monday? Oh, is it Monday? Let me check my calendar.
You are the 13th or 17th?
Let me see. No, 13th. 13th.
13th.
Yeah, 13th. 13th. No, April. 6:30 p.m. So please try to attend. Okay.
Okay.
Mm.
So it will be the last class, I think.
Yeah, yeah.
Okay.
Hmm.
So it ends here.
Yeah, we can discuss it that day.
Okay.
Hmm.
So I'm leaving.
Huh, huh. Okay.
Good night.
Good night.
Bye.
Bye.